Plunge past the familiar macroscopic anatomy of human enamel, cross the microscopic boundary of a restoration, and enter a highly engineered multi-phase chemical architecture. This is composite resin. It is the clinical standard for tooth-colored restorative materials, and it operates entirely as a composite structural system. The architecture relies on two distinct components: a continuous organic phase, known as the resin matrix, and a dispersed inorganic phase, made up of rigid filler particles. Designing this material requires solving a strict physical paradox between how it is placed in the clinic and how it must function in the mouth. During a procedure, the material must remain fluid and pliable enough to adapt perfectly to the microscopic irregularities of a conservative cavity preparation. Yet, once placed, it must rapidly convert into a solid mass with enough compressive strength and wear resistance to mimic the physical properties of natural human teeth. The foundation of the fluid continuous phase is a heavy monomer, typically bisphenol A glycidyl methylacromate, or bis-GMA. To understand why clinical restorations fail and how modern materials survive, we have to deconstruct the nanoscale physical limitations of this base monomer and examine the engineering required to bypass them. Embedded within the bis-GMA resin is a chemical initiator system, most commonly camphorquinone paired with an amine accelerator. When a clinician exposes the camphorquinone to a specific 470 nanometer wavelength of blue light, the molecule absorbs the energy and begins generating free radicals. These free radicals trigger the bis-GMA monomers to link. As the reaction propagates, loose monomers rapidly snap into dense polymer chains. The wide gaps maintained by van der Waals forces convert into tight, rigid covalent bonds. This microscopic tightening causes macroscopic volumetric loss. The entire resin mass pulls inward, a phenomenon known as polymerization shrinkage. If the resin pulls away, it creates a microscopic gap. This allows oral bacteria and fluids to penetrate, a specific failure mode called microleakage. Because this volumetric loss destroys the integrity of the cavity seal, a pure polymer matrix cannot survive as a standalone restorative material. The solution to the shrinkage flaw is the introduction of the dispersed inorganic phase. Manufacturers load the resin with highly rigid inorganic filler particles, typically constructed from quartz or silica. By displacing reactive resin with stable glass particles, you reduce the material capable of contracting. As filler volume increases, there is a proportional rise in compressive strength and wear resistance, exactly mirroring the drop in volumetric shrinkage. Once cured, these rigid glass particles act as structural shields. They absorb massive compressive mastication forces, preventing the softer polymer network from rapidly wearing away. Heavy metal glasses containing barium or strontium are also included in the filler mix, ensuring the final restoration is radiopaque and clearly visible on future X-ray diagnostics. Displacing the matrix with rigid glass solves the problems of shrinkage and weakness, but forcing rigid glass into a polymer base introduces a catastrophic chemical incompatibility problem. The inorganic glass filler is naturally hydrophilic, meaning it attracts water. The organic resin matrix is hydrophobic, meaning it repels it. If left untreated, these two phases naturally repel each other. They will sit in the same physical space, but they will never form a chemical bond. Without a bond, filler particles act as localized stress concentrators. When a occlusal load is applied, the unattached polymer tears around the rigid glass, propagating jagged fractures throughout the resin. The mechanism to link these phases is an organosaline coupling agent. Saline is a bifunctional molecule. One end chemically locks directly into the hydroxyl groups on the silica filler surface. The opposite end contains a methacrylate group. When curing light hits, it polymerizes directly with the organic resin chains. The saline coupling agent acts as the linchpin of the composite. It transforms a loose, unstable mixture into a unified structural matrix, capable of efficiently transferring heavy bite forces from the soft resin directly into the rigid glass fillers. With the phases successfully linked, material scientists faced a strict geometric challenge, balancing the size of the filler particles to achieve both high mechanical strength and high aesthetics. In dental composites, aesthetics are largely dictated by polishability. The smoother the surface, the more it mimics natural enamel reflection. A scatter plot tracks polishability against strength. Macrofills plot high strength but rough. Microfills plot smooth but weak. Hybrids settle for moderate averages. Nanofills eliminate the trade-off. Their sub-100 nanometer clusters polish like a microfill, but pack densely into microscopic gaps, achieving the maximum strength of a macrofill. By mastering this nanoscale geometry, engineers optimized the dispersed phase, allowing composite resins to achieve the rigorous physical properties of natural tooth structure. The final composite architecture is highly specific. A continuous BIS-GMA matrix, optimized nanofillers, an organosilane bridge, and a precisely tuned photoinitiator system. However, this complex chemical web has no natural affinity for human tooth structure. Successful placement requires conservative cavity preparation paired with precise chemical conditioning. Clinicians must use a 37% phosphoric acid etch and a specialized bonding agent to create microscopic retentive tataxing the dentin, mechanically interlocking the composite to the tooth. Furthermore, standard composites cannot be placed in massive bulk. The photoinitiators have a strict depth of cure limit. Blue light cannot penetrate deep, leaving the bottom layer unpolymerized. To overcome this, clinicians rely on incremental placement, carefully building and curing the restoration in small 2mm layers. This layered approach also serves as the primary clinical defense against polymerization shrinkage, controlling volumetric loss and reducing stress on the cavity walls one increment at a time. These specific procedural requirements explain the strict contraindications for composite use, situations with poor moisture control, or massive stress-bearing areas where the brute strength of silver amalgam historically prevailed. Every precise manipulation step in the clinic is a direct accommodation for the underlying molecular physics of the material. As material science advances towards smart bulk fill innovations, engineers will continue to rewrite the structural rules of restorative dentistry.